American Women in Mathematics. This is for anybody. I will send out more information about that as well. We have a colloquium today at 1 p.m. in Reggae, one homework problem exemption. You can use whatever you want. You can save it for future classes. You cannot redeem it for cash. You cannot transfer to other people. If you do the Putnam, it is 6 hours of problems, 120 points. 1 point out of 120 is a great score. You get 2 homework problem exemptions for each section that you try. But you cannot use those exemptions until you actually take the Putnam, which is in early December. So it may not be that useful for this course, but if you ever take another class from me, you can keep those in the bank. And I have had students who have saved them up until their senior spring. And it's a teaching, Professor Miller. Okay, can somebody hit record on that one over there? All right, so hopefully this will work well. Interesting. It's not. It is hidden somewhere. Interesting. It's not letting me switch screens to. Weird. Oh, here it is. Okay. All right, so here's a quick outline. So I'm going to do some of these things a little bit faster than I did in the previous year. If you want more details, just look at last year's video. I want to try to free up a little bit of time to do some programming early in the semester. So I'll talk a little bit about Russell's paradox. I'm probably not going to talk today about building up the integers from the empty set. If you want to see how you can build all the natural numbers from nothing, you can just watch the video. I'll talk a little bit about probabilities of items. I'll talk very briefly about Fubini's theorem and why it fails. And then the goal is not to be hard to go through and talk a little bit about our wish list for probabilities. So the first now is, I think I have to actually always go through the share and always tell it which screen I want to share, which is annoying. Okay. So the first thing I had was Russell's paradox. Let's just make this a little bit larger. Okay, so one of the key tools is set theory, and we need this to build up a rigorous notion of probabilities. Unfortunately, it is very easy to start to create a theory for sets and run into some contradictions and problems. Out of curiosity, how many people have heard of Russell's paradox? This is one of the great oh shit moments in mathematics. So Frege here just developed this monumental work on set theory, and the story is Russell's regression. But what about the following? And it was a fundamental contradiction in how set theory was created. And so Russell says, let's let R be the set of all x such that x is an element of x. Most things are not elements of themselves. Okay? If you look at the set of all natural numbers, the set of all natural numbers is not itself a natural number. If you look at, I'm not going to keep going on. I think this is pretty clear. So let's look at this. So once you have this set, it's natural to start asking certain properties about the set R. And this is a fun lecture to give with a Boston accent. What might you want to know about R? Yes, how many elements? So one is, how many elements does R have? In particular, which element might you wonder is an element of R?
Whether R is.
Yeah, so this is why it's great to be Boston. Is R in R? Case 1, yes. Well, if R is in R, oh sorry, this is all elements x such that x is not an element. I fixed it. Sorry. It's all x such that x is not an element of x. Sorry. Said the right thing, but wrote the wrong thing. R is the set of all things that are not elements of themselves. So we could ask, is R in R? Well, if R is in R is the collection of all things that are not elements of themselves. So if R is in R, then we get implies R is not in R contradiction. So obviously, R is not in R. But let's just see what would happen anyway. Case 2, let's say it's not in R. Well, if R is not in R, R is a collection of all things that are not elements of themselves. Therefore, since R is not an element of itself, R must be in R. Implies R is in R. Contradiction. So if R is in R, thank you, we're going to have to deal with it. No, I appreciate you closing out. So we're in a ridiculous situation that R is in R precisely if it is not in R. What this means is our notion of set theory is faulty. You cannot just take a collection of all objects that have a given property, put them together, and say that's a set. There are specific rules about what can be considered a set. And there's specific rules as to how you can use things such as is an element of. I'm not going to go into too much detail on this. This is a first course in set theory. We're going to, for the most part, do things at an intuitive level. But I want you to be aware of the need for advanced theoretical mathematics. That there are a lot of very simple statements. One of my other favorite statements is the Banach-Tarski paradox. Take a solid sphere, let's make it of gold. There's a way to chop it into 5 disjoint pieces, such that if you pull 2 pieces aside and just translate and rotate them, they will assemble to a complete solid sphere, same size as the original with no holes, and the other 3 pieces can be assembled to the same size with no holes. So you can essentially double the volume of the sphere by making these strange cuts. And then allow them to repeat, and you can get as much gold as you want. Now, these cuts are strange. They cannot be described. They use what's called the axiom of choice, in fact, the uncountable axiom of choice, which I don't really like. I think it gives too much power to mere mortal mathematicians. Other colleagues of mine have no trouble assuming that. Oh, yeah. Let's take that as one. I will see if I can talk to the college about not having them roll along during class hours. You know, does anybody live in this building? Oh, you could all tell them to just go to like 6 a.m. You have to be very careful about what axioms you use to build your theory. And this is trying to tell us we have to be careful. For the most part, if we look at finite sets, so A lives in some space omega, then maybe the probability of A might be the number of elements of A divided by the number of elements of omega. This is a good way to deal with nice situations. So for instance, if I want to know what fraction of numbers are prime, I might look up to a certain height and count how many numbers are prime, how many integers, take their ratio, and that will give me the fraction of numbers that are prime. If I choose a number uniformly at random, this will be the probability I choose a prime. If I look at even numbers, what should I get for the probability of an even number? What do you think you would get from evens?
It'd be 1/2.
It would be 1/2. Unless, well, maybe I stopped at an odd number, but it should be approximately 1/2. And if I stopped at the right point, it should be exactly half. That's the level that I need us to be able to look at. Now, we do want to talk about countable versus uncountable infinities. Firstly, how many people have seen countable sets before? Okay, so a countable set means you can put it into a one-to-one correspondence with the positive integers. Or you can do it with the non-negative integers. Or you can do it with all the integers. And so this would be sets like, x1, x2, x3, ... I would have some sequence of numbers. And the whole point about countable is I have this ordering of every element. And if you have a favorite element, maybe it's 196, and there's a reason why I'm choosing 196, but I don't have time, then I can tell you when you will hit that. It might be complicated, it might take a while, but you can get to it. So for instance, the rationals are countable. And so here, is a way to do the rationals. So what I'm going to do is I'm going to just make a little grid of integers. I'm going to look at all the points that have non-negative coefficients. All right, so I'm not going to bother, doing them nicely. So over here, this will be the point 1, 1, followed by the point 2, 1, followed by the point 3, 1, followed by the point 4, 1, and so on and so on. The next row, this point over here would be the point 1, 2, 2, 2, 3, 2, 4, 2, and so on. Each one of these is going to be a rational number. This is going to be the number 1. I'll do 1 divided by 1. This will be 2, 2 divided by 1. This will be 3, 3 divided by 1. This will be 4, 4 divided by 1. This number over here, this is 1, 2. What number should that be? 1/2. And then I have the point 2, 2, which is, so I'm actually going to represent some numbers multiple times. That's fine. And what I can do now is I can actually go through all of the points. And so I can go through them in lines. I could go through like this, and then this way, and then this way, and then this way. And you can see that I'll get any fraction I want. And I can actually calculate, I can write down the formula when I will get to it. If I want to figure out when do I get to 196,1, I can figure that out. I don't want to, you don't want to, but if our lives depended on it, we can do that. If you want to know when you get to 17/93, again, you can do that. Okay? Or you could say, you know what, if I get to a number that I've already had, let's skip it. We could do that. You could also do other types of methods to go through this. It doesn't really matter what method you take. The main thing about countable is there is a way to walk through the whole set. And you know when you will get to a certain number. Those will be the only infinities we look at that are discrete. We will not look at uncountable infinities. We can't actually handle those. All right. And then, so the next thing I want to just briefly mention is Houdini's theorem. You should have seen this in multivariable calculus. This is one of the big things we have in the integration section of multivariable calculus. You really have two things you can do. You can switch the order of integration, and what's the other thing you can do to evaluate a double integral or triple integral that is not working out? We have two techniques, switching orders Let's say I want to integrate something over, I don't know, a sphere. What might you do? What might you change it to?
Polar coordinates.
Not for sphere. Spherical coordinates, right? And if you had a cylinder, and if you had a circle, yeah, we don't say circular coordinates, we say polar coordinates. So the other trick you have for multivariable calculus is change coordinate systems. If you have spherical symmetry, use spherical coordinates. If you have cylindrical symmetry, use cylindrical coordinates. This is not a class in multivariable calculus. Most of the time, we're going to just have very simple integrals to do because I don't want to overwhelm you with the calculus. I want to be emphasizing the probability and the statistics ideas. So for the most part, we'll have very nice integrals that are going to be from A to B and from C to D, a nice rectangular region. Okay? If you want more painful integrals, I'm happy to oblige, but I don't think you do. Yeah, I'm seeing you just look at We want to be careful though about Houdini's theorem. And so essentially, if you had to boil down to why do you take real analysis classes like this, it's so that you can work with infinities without making a mistake. Physicists have a very good intuition as to how to deal with infinities and things that explode. In mathematics, whenever you have an infinity, that's a danger sign. So for Houdini's theorem, when can you switch the order of integration? So what I'm going to do is I'm going to just color my dots. And if I color it red, it's going to be +1. If I color it blue, it's going to be -1. And so on and so on and so on. And these go off to infinity. Okay? So if I look at the sum in each column, what's the sum of each column? Imagine, this goes off to infinity. What are all the column sums? Yeah, it doesn't matter what column I choose. Each column sum is 0. So if I sum over all the columns, I get 0. What about the row sums? What is the sum of the first row? 1. And what's the sum over every other row? So if I do row sums, what do I get? So here's a situation where, depending on the order of summation, so in the first one, I first chose a column, summed over the column, and then summed over the rows. And if we do it that way, we get 0. If we do it the other way, we first pick a row, sum over the rows, we get 1. Order matters. And what's going on here is if you take the absolute value of the function and just summed it, you would get plus infinity. There's an infinity lurking. Okay? I don't want to go into too much detail for Fubini's theorem. This is hopefully something you've seen. In order for us to be able to use it, I really need not to have an infinity going on. My space here is infinite. The value of my function is plus or minus 1. This is bad. If you are upset because calculus normally looks at nice functions that are continuous and these are points that are separated, what you could do is you could smear things out. Instead of having it be all concentrated at a point, what you could do is maybe draw a little box around one of the points and just smear it out around the box. Maybe make it like a tetrahedron coming out and do something like that. Okay, so this is Fubini's theorem. All right. The next thing I want to do is talk a little bit about a probability wish list. Okay? You can define anything you want. And it took a while for people to come up with what do we want the definitions to be for probability. How many of you have taken measure theory, which is a graduate level math class? Okay, that's where we really need to do things with full rigor. I am assuming nobody is eager to learn measure theory between now and Friday. This is a safe assumption, I think. We are not going to do things with full rigor. We are not going to do things with sigma algebras and whatnot. You should be aware that such stuff like this exists. If you want to have a little bit more detail, you can look at the book. You can look at the video online from last year. We are not going to really use that in this class. We're going to keep things at the intuitive level of, we know what a probability is. If it's a discrete thing, how many times do we have it divided by how many possibilities there were? If I want to roll 2 fair die, what are the possible values for the sum? 2 fair die.
2 to 12.
2 to 12. There's one way to get 2, 1 on each die. One way to get 12, 6 on each die, and there are 6 ways to get a sum of 7. The first die can be anything, and then the second die is forced on you if you want the sum to be 7. So the probability of rolling a 2 is going to be 1 out of 36. The probability of rolling a 7 is going to be 6 out of 36. Not surprisingly, if you sum all the probabilities, you get 1. Okay. This is the level of intuition I want you to have for this, but I just want you to be aware that we do need to be careful. So we have an outcome space omega, and we have an event A. What should be true about the probability of A? Yeah, between 0 and 1. Is in the interval 0, 1. Should be a real number between 0 and 1. What about the probability of A complement? So A complement is the probability that A doesn't happen. Yeah, that should be 1 minus the probability of A. These seem to be very reasonable things to insist upon. You may have occasionally heard about giving 110%. I know some of you play sports. Just say, yes, coach. Okay? Don't want to get into a mathematical discussion with your coach. If you do and you get into trouble, have your coach talk to me. Okay? Is it possible to give 110%? Now, there are certain things in chemistry you might have that's super saturated, where if you start off at a different temperature or pressure, you could actually have more dissolved in it than you could normally at that lower temperature pressure. And then as you lower things, and what we're talking about, you're not going to have something happens 120% of the time, or something happens negative 30% of the time. Our probability should be between 0 and 1. The probability of A and A complement, they should add up to 1. And now, say the AI are distinct events. Oops. Okay, say the AI are distinct events. The probability of the union of the AI, what do you think that should be if we have disjoint events? 0 is a little bit extreme. Yeah, so the probability of the union should be the sum of the probabilities if they're disjoint. You always want to make sure you don't double count. When we had Bird playing Magic, what's the probability Bird wins? It's the probability Bird wins on his first shot, plus the probability Bird wins on his second shot, plus the probability Bird wins on his third shot. These are disjoint events. Can Bird win on both his first and his third shot? Can Bird win on his first and third shot at the same time? No. There can be a game where Bird wins on his first shot, there can be a game where Bird wins on his third shot, but there's not going to be one game where Bird wins on his first and third shot. You don't continue to play once you've won. Kind of like the old adage, it's in the last place. It's always the last place you look. As George Carlin remarks, yes, what idiot goes, I found it, now I wonder where it could be. Right? You stop once you find it. There are times when you would want to continue to look after you find something. Can anybody think of why you might want to continue to look?
Find all cases?
No, let's say there's only one of the objects. If you are being observed and you do not want somebody to know that you found something, or you don't want somebody to know what you were really looking for when you're doing like a web search. There's a lot of good espionage stuff like this where you continue to look to give people a false sense of what your goal is. Okay? So this should be the sum of the probabilities of the AIs. These seem to be a very reasonable set of wish list items. It turns out they are incompatible. It is not possible to have a notion of probability that satisfies all of this. You are wishing for too much. But this isn't terrible. You are already used to disappointment, right? I mean, let's look at f divided by g and take the derivative. If you could choose mathematics, if you had the wand, what would the derivative of a quotient be? What would you choose it to be?
1.
No, you want every quotient to be 1. That's really restricted in your way.
I'll probably go 0.
Yeah. That's a bit too restrictive. But what would be a reasonable restriction to say, I want the derivative of a quotient to be... Yeah, wouldn't that be much easier to remember than the real quotient rule? Okay. Okay, this is not the quotient rule. We'd like it to be, and as a nice exercise, find all functions f and g such that f over g prime is f prime over g prime. But no. What's the problem for us? The problem is uncountable union is the problem. It's okay if the union is countable. And one way to look at this is imagine, a sub x is the point in the interval 0, 1. Okay, so imagine ax is the point x in 0, 1. So then if you take the union of all the ax's, you get 0, 1. Each ax should have the same probability as all the other ax's. I should assign a probability of 1 to 0, 1, but because I have this uncountable infinity, things are going to just be disastrous. no probability that I assign to the AX is going to work out. And so I go into detail in this in the last lecture. This is in the book. I don't want to spend too much time on this. I want to spend more time on just writing some computer programs. But the issue is that if we have uncountable unions, it's bad. Okay? Countable unions is fine. Okay? I think that is all the theoretical stuff I wanted to do. Yes. Okay. So now I'm going to stop the share. And then I will just do very quickly, we'll do some computer programming. So I got a call from a friend who, sadly, their father recently passed away. They have two brothers, and they need to divide the estate. And the father has given the different kids different amounts of money over the years, as well as giving the business partner of my friend some money. They now need to divide it. And this is how my friend analyzed things. So he said, yeah, here's how much money each person has. One person got 60,000, she got 60,000. One of the brothers got 583,720, another got 45,000. I'm sorry. One brother got nothing, and then the business partner of the first person got 45,386. And they wanted to figure out how to allocate the money. And so this is the discussion my friend sent me. And then they said that they'll look at the loans as how much each person has, calculate giving back 1/3 of the loan, because when you have a loan, you have to give some of it back, and trying to calculate how much this all is and whatnot. And then they keep doing all the analysis, this is what percentages of things are coming out. And then in the end, they figure out how much each person has. And they said, I know the math is right, and I am in terror of explaining this to my brothers as to who owes how much. Can you come up with a cleaner way to explain this? And this is one of the key things I want you to get out of this class, is how do you explain things? You can hit pause, or I'll email the sheet. So here's my simple explanation. The father has made a couple of loans over the years. So this is how much money the father has distributed. Here's who's gotten what. Each person should get 1/3 of the total. And now let's just have the person, the business partner, we were told they were going to just give the money directly back to one person. So let's just credit them with that, and then just figure out the new amount. So I will know very shortly if this was convincing for when they talked to their brothers in terms of dividing up the estate. I told them that my fee is 0.01% of the father's estate, so it's about $100. So I will be paid in General Tso's chicken, hopefully, as well as the ability to use this as examples in probability. So I'll send this to you, and the point is, how do you explain things in a way that people can follow? And just because you understand this calculation doesn't mean others will. Almost surely, at some point in your life, you will have a boss who knows less math than you. And you need to convince the boss who can say yay or nay that they should go with your recommendation. And so how do you present the information clearly and cleanly? All right, so we have half of the class, a little bit less than half the class left. What I want to do now is I want to shift to mathematical programming. So I'm first going to do a program that I wrote at home. I know it works, and I'll try to program something live in front of you. So I will do the birthday within a day. So this is what we have. How likely is it that with 12 people, there's actually a 13th person who hasn't been able to reach Williams yet, they're having issues traveling. So the class is a little bit larger. I debated asking them when their birthday is, see if we actually would have won. So I want to calculate what is the probability if you have a certain number of people that you have 2 people with a birthday within a day. Well, I'm going to do this with a numerical simulation. Rather than calculating it theoretically. Theoretically, it's actually a little bit challenging. If you have somebody born on day 2, they kill days 1, 2, and 3. If somebody's born on day 4, they kill day 3, 4, and 5. You've already killed day 3. If they had been born, however, on day 5, that kills days 4, 5, and 6. So depending on when they're born, those 2 people could either kill 5 days of the year or 6 days of the year. The problem is far more involved to come up with a closed form theoretical answer. But if I do 1,000,000 or 1,000,000,000 simulations, and I see that the answer seems to be stabilizing, yes, it's possible that my answer is very far from the simulation, but the probability of that is so small It will be more likely that I will be showing up in class after having won the lottery 4 times in 4 different states on the same weekend and wearing the New York Yankees shirt. Okay? It's not gonna happen. Okay? So if you can simulate, that's great. So I'm gonna use Mathematica. I do not care what language you use. I have some videos online that tell you how to use Mathematica. I want to talk a little bit about the coding here. So the first is I name my function, birthday within a day. A question or no? Okay. So the function is called birthday within a day. You always want to have good descriptive names. The underscore here means these are 2 variables. The variables are num_do and num_people. And then module means I'm starting things. I have a bracket here which starts, and then let me just move this out of the way. It comes all the way down here, and that's the end. You will notice that there is text over here between parentheses star and star parentheses. These are comments. For those of you who have ever programmed without using comments, please stop that habit. I will admit that when I'm writing code for myself, I'm often bad, and I often don't bother putting in comments. If it's a really short program, fine. If it's a long program and somebody else might need to use it someday, please put in comments and explain, there's this special case that I must remember, and this is why I'm doing it this way. If you have short code and you're doing something in LaTeX and you need to generate an image, store your computer code inside your LaTeX file and just comment it out. And then if you have to change the image, you've got this source code already there to regenerate. Whenever I do begin and ends of statements, I like to write them immediately. So the first is I'm going to just count how many successes I have. Every time I have a success, I'm going to increase success by 1. I'm going to do things, n goes from 1 to num_do, and n increases by 1. This is the main loop. And so if I want to figure out the success percentage, it's just going to be success divided by num_do. And so here, this brace over here, this means the begin of the end loop. And then if I scroll down a little bit over here, this is the end of the end loop. In fact, over here, I should have written end of the end loop. And that just makes it clear what's going on. And then this is the first code to figure out what's going on. So k goes from 0 to 366, I set a sub k to be 0. I'm going to let a sub k denote how many people have a birthday on day k, or a day before, or a day after. We will assume there are no February 29s. And I'm actually defining this a little bit more than I need. I really only need 1 to 365. I'm overflowing it a little bit just so that if I accidentally call something in, it's not going to break down the code. If you can, have a little redundancy, a little protection. And then what I'm going to do is p goes from 1 to the number of people in steps of size 1. This begins the p loop. And then if I scroll down, this is the end of the p loop. End of the p loop. One thing that's nice about Mathematica is it actually indents as you go. So it makes it much easier to just look at the code and see, here's the for loop here, it indents all the way here, it ends indent here. This is all the p loop. So x is a random integer from 1 to 365. This is just the command in Mathematica to choose an integer in that set. And then what I do is, now that I've chosen the integer, I increase the number of people who have a birthday on day x by 1. ax is equal to ax plus 1, just increase it by 1. If you had a birthday a day after, I increase that by 1. If you had a birthday the day before, I increase that by 1. Now the problem is, if you have somebody who, if I choose x equals 1, then that goes to 0. And so just to be extra safe, if x is 1, I'm going to make sure 365 is increased by 1. And if x is 365, I'm going to make sure that 1 was increased by 1. And then within 1, will just let me know if I have 2 people who have a birthday within 1. So after I finish putting in all the people's birthday, if p equals 12, I do this 12 times. I then go from 1 to 365, and I look, and I see if a sub m is greater than 1, then I set within 1 to be 1, and I know we have a success. And then when I'm done, I just say if within 1 is 1, I increase success by 1, and then I just print out success divided by num_do. So this will work. One of the nice features of Mathematica is you can do something called timing, and it will tell you how long it takes to do it. So to do 100,000 people on my computer, it actually took it 95 seconds. And then to do 1 million people, it took 967 seconds. So about how long is 967 seconds?
2 minutes.
Yeah, it's not too bad. 3,600 seconds in an hour. But it's a sizable enough time that I hadn't run, then went to the math colloquium to grab pizza and say, this is the stuff I can advise colloquium on, listen to how you give a colloquium talk for the 11th year in a row, and then come back and see, oh, good, it finished. 15 minutes is long enough that you can't just quickly rerun it. So if you can get the time down, that's good. It's not horrible, it's not great. Does anybody see any inefficiencies in the code? Anything we could do better? Yes?
There's like a few places that you can optimize. Like
Okay.
For example, one of the places is in the loop.
Yes?
You can check if they're within one of someone already in there, and that'll make it a lot faster.
And as soon as you find that
Yeah,
somebody's within one, what do? Then you abort. Right? So what we're doing here is, this is fine theoretically. I go through everybody. But once I have 2 people that are within one, does it really matter what other birthdays I have? No. You stop at that point. Now, sometimes you go like, we're not little kids here, right? Once we have a success, we can stop. So this is one of the most common mistakes people make when they're coding. It's not really a mistake, it's an inefficiency. If you only care about seeing that something happens, as soon as you see it happen, abort the program. So this took on the order of 15 minutes, it took 967 seconds. So when I program it a little bit more efficiently, so what I now do is, if any one of these values is greater than 1, I declare success to be success plus 1. I let P be the number of people plus 1,000, so I break out of the P loop. And you get very similar percentages, but now, instead of taking 967 seconds, it only took 582 seconds. So it still took a decent amount of time, but you saved a respectable amount. Okay, any questions on this? So again, I don't care about what environment you use for coding, but what I want you to see is that you can do some very simple coding. There's a lot of great stuff you can do. Let's do a card game. All right. I just want to try to make this large so we can see it. So what do you think I'm trying to calculate in 2 king, 2 queen? Yeah, the probability I draw. I'm more specific.
Like a king of a red one, like a particular color.
No. Yeah, there's a lot of things you can do. Yes?
Probably of drawing 2 kings and 2 queens.
It's probably drawing 2 kings and 2 queens. I could put in another thing as to the size of my hand. And so this can just give you a little bit more flexibility. I'll just put in hand as another parameter. I might want to just do hand equals 5, but if I hard code 5, if the professor says, oh, I'm sorry, we were doing 7 card stuff. And instead of doing some hand motion to your professor, I said, fine, I'll just run the program with hand equals 7. So always put in parameters like this if you can. So I do module. Oh, great. And then for some reason, it sometimes likes to change the font size. And so this stuff over here just means I have no local variables. And so I'll do just as before, I'll have success be 0. I'll just keep track of how many successes there are. In the interest of time, I'm probably not going to put comments in right now. So the first thing is I need a deck of cards. Now I could have the numbers 1 through 52. 1, 2, 3, and 4 could be my aces. 5, 6, 7, 8 could be the kings. There's a much better way to do this. So deck is equal to 1, 1, 1, 1, 10, 10, 10, 10. And then for D equals 1, D less equal to how many more cards do I need? 44. I don't know why it's so small. D plus plus, dec equals append to dec 0. And this is one of my favorite tricks. If you have a king, you can sum the hand that you get. A king is worth 1 point, a queen is worth 10. What must be true to have 2 kings? I'm sorry? I had the kings as 1. Right? I'm sorry? No, because 0 is an even number. The 1 digit has to be a 2, 3, or 4. If the kings are worth 1 point, so king equals 1, queen equals 10. If I have 1 king that's going to contribute 1 to the units, to the 1's digit. If I have 2 kings of 2, 3 kings of 3, 4 queens of 4, I just need to check and see, is my 1's digit at least 2? What about queens? I just need to make sure that the 10's digit is at least 2. That's much easier than checking to see which cards there are. So depending on what problem you're doing, you can often code things very nicely. And so now, okay, so now what I'm going to do is the main loop. So for n equals 1, n less than equal to num do, n plus plus, end of n loop. So I wanted to immediately end the n loop so you know what's going on. And now what I need to do is I need to choose a hand. So I need to choose some number of cards from the deck. So there's a lot of ways to do this. One is to look up what functions do I have. So random sample gives a pseudo permutation of a given size. So let's do this. Random sample 1, 2, 3, 4, 5, 6. Now choose 4 elements from that. And so you put your set in first, and then you choose the number of elements. So my hand, so instead of maybe hand, this could be maybe hand size. So hand is equal to random sample from the deck, and I take this many points. And then if the sum, so this is how I would choose the ith element of hand, and I sum I goes from 1 to hand size. So let's just let hand value is going to be the sum. So this is better coding. This is a quantity I'm going to want to use. So let's just let this be the sum of the cards in my hand. And then if hand value equals 22, or hand value equals 23, or hand value equals 24, or hand value equals 32, or hand value equals 33, or hand value equals 34, then success equals success plus 1. There are more efficient ways to code this. I don't want to do the more efficient way. I want to just do it out like this the long way so you can just see what's going on. And then that's all I think I need to do.
You also have 42, 43, 44, right?
Oh, I forgot those, yes. Thank you. So I need to go over here, and then it's going to be bad. So hand value equals 42, or hand value equals 43, or hand value equals 44. And this actually shows the danger of doing things the way I did, is that you could actually miss something. You know, when I was coding this quickly in class, I missed some of these cases. Rather than, I'll just try to fill it in that way. Okay. And I think that will now count. Okay. This is a formatting issue. Okay. So I think that's all I need to do now. And now what I can do over here is I can just print 100 times success divided by numdo. I'm going to just put in the percent sign just so it looks nice. And so now let's do 2 king, 2 queen. Let's do it 10 times. Let's do a hand of size 5. Always do a small value first, just in case you have an error and it starts going crazy when you evaluate and you can't abort. You should also save before you evaluate anything. So just trying to show good programming habits. So now let's try running this. This is always, okay, so it said 0%. Seems a little strange. Still strange, 0%. 0%. I can put a timing on this.
I think there's a space in the add value on 23.
Ah, thank you. Okay,
Is that it?
yes. All right. And then I'm going to put it as 100.0, so it converts it to a decimal. Are people still able to see it down here? So are you surprised by the percentage? Yeah, that's 0.1%. Now it's running pretty fast, so I can make my hand a little bit larger. Are you surprised? Or is this a reasonable percentage? You have 5 cards. I want to have at least 2 queens and at least 2 kings.
Pretty rare.
That's pretty rare, okay? So I'm not so surprised. Let's do it 10 times, and let's take a hand of size 52. Okay. Are you surprised? Extreme cases, this is like extreme sports. Extreme probabilities. If you do not get 100% there, something is wrong. Or you have one hell of a magician. What if I went down to 50 cards? Do you think it should still be close to 100? Yeah. And in fact, it's so close we're not even seeing the difference now. Let's go down to 40. Out of 40, now it's dropping to 90%. Now, as a nice exercise, calculate what the answer is. And now you have to go, is it easy to calculate the probabilities of all these events, or to calculate the probability of having no queens and no kings? Exactly 1 queen, which is the easiest way to do the calculations? Lots of ways you can do it. But you can simulate the answer without too much trouble. And this is the power of coding. This is the level I want you to be able to do in this class. I'll send links later today about how to do more stuff here. All right, any questions? All right, if somebody could hit the stop button on that.